Hey everyone, welcome back. I had that video I made. It's not an official lecture, but it was sort of a review or an introduction to, however you want to look at it, complex numbers. And so let's pick up from there. I said that we needed to learn complex numbers because it gives us some important groups, some interesting, worthwhile new groups. And so let's just start with an example. So let's let U equal the set of all complex numbers, so the set of all z in C, such that the modulus of z is equal to 1. U is called, right, so U is the unit circle in the complex plane, right? So if you want to draw the picture, right, U, right, if you take all complex numbers that have modulus 1, what it does is it fills out a circle of radius 1. Now, if I take a couple of complex numbers that live in U, so let's say if Z and W are elements of U, then if I write them in polar form using the exponential form, right, since each modulus is equal to 1, then what we know is that Z equals e to the I theta, and W equals e to the I, I need another letter here, what am I using? Phi is fine, I guess. Okay, so e to the I phi for some angles, theta and phi, right? So some numbers between 0 and 2 pi. So now, if we do Z times W, that's equal to e to the I times theta plus phi, and what you're supposed to notice is that this right here has modulus 1 also, which means that it's an element of U. So what did we just show? We showed that U is closed under multiplication. Multiplication of complex numbers is definitely associative. Let's say complex multiplication. That's especially easy to check if you use the polar form of complex numbers. So complex multiplication is associative. If you want, you can, maybe it's worthwhile to grind it out, but we're not going to do it here. So complex multiplication is associative. Maybe you can see where I'm going with this right now. I'd like to show that capital U is a group. And so I've shown that it's closed under its operation. The operation will be complex multiplication. We know then that the operation is associative. The next thing we need to do is identify the identity element, or an identity element. And who's that going to be? Well, the number 1, which is e to the I times 0, is an element of U. And if you do 1 times Z, that's equal to Z, which is equal to Z times 1. And so 1 is an identity of, or for, capital U. The last thing we need are inverses, and so if Z equals e to the I theta is an element of U, who's the identity, who's an inverse going to be? So Z prime equal to, so let's see what I need. I need somebody so that when I multiply that somebody times e to the I theta, I get e to the I times 0. And so Z, and I write this out, e to the minus I theta is an inverse for little z. What's our conclusion? Our conclusion is that U is a group. Under, I gotta write it better. I need to write it like this. U, comma, let's put a dot there, is a group where dot is complex multiplication. We typically don't use a dot, but I need a symbol if I'm going to use this ordered pair notation. So where dot is just complex multiplication. Now let's try another example involving the complex numbers, right? But here we've developed a new group, right? One that we didn't know about before. And here comes another one involving complex numbers. So for a natural number, so for say n in natural numbers, let capital U sub n equal the set of all z in C such that z to the n is equal to what? All right, so here's some collection of complex numbers. It's a set of all complex numbers that satisfy that equation right here. And what we're going to do is show that U sub n is a group for every choice of n. That's going to give us an infinite number of groups. So we need to get a handle on who the elements of U sub n are. So let's write z using our polar form, z times cosine theta plus I sine theta. Then z to the n is equal to the modulus of z to the n times cosine n theta plus I sine n theta. And then we're setting that equal to 1. We want it to satisfy this equation. So that's going to equal 1 times 1 plus 0i. So now that's going to give us 3 equations. First of all, the modulus of z to the n has to equal 1. Cosine of n theta has to equal 1, and sine of n theta has to equal 0. Right? It leads to these 3 equations right here. So let's see, when does that occur? All right, so it follows that so let's see, when does this one occur? It occurs at 0 and 2 pi, plus or minus 2 pi, plus or minus 4 pi. So this would tell us that n theta has to equal 2k pi. When is it equal to 0? It's equal to 0 at all multiples of pi. So we can say and n theta has to equal not just the even ones, but so we could say it's also equal to L times pi. But to make it happen simultaneously, we don't actually need this one. And so that's the one that's true. And so that means that theta has to equal 2k pi over n. Hopefully it's clear why I was able to just cross this one out. We need these both to happen simultaneously. We need n theta to be an even multiple of pi, an even multiple of pi, and we need n theta to be a multiple of pi. Well, to have both of those occur, we need n theta to be an even multiple of pi. Right. Okay, so if the modulus of z is equal to 1, right, that tells us that, if the modulus raised to the nth power is equal to 1, that tells us that the modulus, because it's a positive number, has to equal 1. So we can say thus, z is equal to 1 times, how am I doing this? Yeah, cosine of 2k pi over n plus I sine 2k pi over n for k in. Now, who are k going to be? Well, officially k needs to be an integer, but it's really k equal to 0, 1, 2, all the way up to n minus 1. Once you get back to n, it's going to repeat itself. So this collection of values for k gives us all possible solutions to that equation. Using the exponential form, we get z equals e to the 2k pi I over n, where k equals 0, 1, 2, up to n minus 1. Right? So there are exactly n solutions to that equation, which means that u sub n, capital U sub n, consists of exactly n elements. Now, so letting zeta equal e to the 2 pi I over n, we have un equal to zeta to the 0, comma zeta to the 1, zeta squared, all the way up to, oops, that's a funny looking zeta. I used to practice my Greek letters quite a bit, right, so that I can make them look nice. So if you need to practice your zeta, look something like that. Right. So that's the point to notice is that the solutions to this equation, right, are of this form right here, and we can express them if we take e to the 2 pi I, that's when k equals 1, and then when k equals 2, that's just going to be zeta squared. When k equals 0, it's just going to be zeta to the 0. And so we can see that they're all multiples of zeta to the 1. Now, with the operation of complex multiplication, which I'll use that same symbol, little dot. So u sub n comma dot is a group. So that's my claim. And then we need to go through quickly and check that that's true. Complex multiplication we know is associative. If we multiply two elements of this form, we're going to get another element of this form. Identity is 1 right there, right? Zeta to the 0. And then, all right, let me write these out instead of being so hand wavy. So note that U sub n is closed under multiplication. And so here's the idea. If I take zeta to the k times zeta to the m, I'm going to get zeta to the k plus m. Now, if this sum right here is greater than n plus 1, what happens? Well, it just cycles back, right? And it'll give us some other element in here. What else do I need to say? Complex number or complex multiplication dot is associative. 1, which is zeta to the 0, is an identity. And then the inverse, so an inverse for zeta to the m is zeta to the n minus m, right? If you multiply these together, what do you get? Zeta to the n, which is exactly the same as zeta to the 0. Okay, so we've got a group here, and so this group has a name. So within the operation of complex multiplication, UN is a group called the group of nth roots of unity. All right, so here's another example of a group. Here's another example. So let's let z sub n equal the numbers 0 up through n minus 1, 0, 1, 2, up through n minus 1. And I want to give an operation, so let's let plus sub n be the operation on z sub n defined by a plus sub n b is equal to a plus b on n. All right, so it's the operation of just addition modulo n. So I'll just say check that Zn with the operation of plus sub n, right, addition modulo n, is called a group. So this is a group called the group of integers into integers modulo n. So I'll leave that to you. Go ahead and go through the steps here to verify that this actually is a group. Now I've been using this ordered pair notation when I'm talking about groups, but that's really not standard. That was just to get the ball rolling. Typically, when we work with a group, we don't actually write it in ordered pair notation. We will just say let G be a group. So the standard notation, and this is the notation that we are going to adopt now. So notation, when referring to a group, we will no longer use the pair notation G comma star. That's how we would do it in the abstract. Instead, we're just going to say let G be a group. So instead, we will say let G be a group, and it'll just be understood. Whenever you're talking about a group, there's a binary operation that goes along with that. In many cases, I mean, in fact, we won't even need to write this star. Every once in a while, if we need to be very specific, so we'll say, if necessary, we will add the words, so if necessary, with operation star. But in most cases, we won't even need to say that. We'll just say let G be a group, and it'll be understood. There's an operation. If I need to use the symbol star, I'll use the symbol star. But it's it just gets a little bit cumbersome to even include this. We know if there's a group G, it's got to have an operation. Now, in most cases, or in many cases, right, as we start building up our list of familiar groups, the operation is going to be understood. So we'll say in many cases, we won't even need to specify the operation anymore because we've already seen that particular example and we know exactly who the operation is. So in many cases, the group operation will be understood. And so these ones right here are standard. When we talk about Z, so Z means the group of integers with the operation of addition. Z means, so I'm just going to write it like that for the last time, right? From now on, when we talk about Z, we automatically, unless otherwise stated, the operation on the integers is addition, right? Same for Q, R, and C. If we write these symbols and we're saying we're talking about the group of rational numbers, the group of real numbers, or the group of complex numbers, automatically, by default, we understand that to be addition as the operation. If I write Q star, that means Q star, remember that's all non-zero rational numbers, with the operation of multiplication. So in Q star, when we say the group Q star, we're talking about that group along with multiplication as the operation. Same for R star and C star. Right? So if we talk about R star, we mean the group of non-zero real numbers with the operation of multiplication. Some more standard symbols for groups. Those are ones where we're not even to specify who the operation is. We all know who it is. So our next example, U means the unit circle in C under complex multiplication. U sub n means the group of units, the nth roots of unity. So it means the group of nth roots of unity under, right, multiplication of complex numbers. And one more, Zn, means the set 0, 1, 2 up through n minus 1 together with the operation of addition mod n. All right, so from now on, if we work with any of the groups that you see here, Z, Q, R, C, Q star, and so on, right, the operation is going to be understood. And now, let's look at some more examples of groups. And in some of these, we'll check the axioms in full detail, and others I'm going to leave them as exercises. But what we're really trying to do is build up our list of examples of groups that we'll then be looking at for the rest of the quarter. In fact, really, some of these we'll be looking at for the rest of the year, for those of you that are going on for all 3 quarters. So, some more examples. So let's let S be the set of, so I want all functions from Z to Z. Okay, so there's our set, and we want to create a group, so it'll be under the operation. So under addition of functions. And so how that's going to go, so if we have 2 elements, so f plus g, what that means, so that's a new function. And how is it defined? It's defined as f of x plus g of x. Okay, so who is our set? Our set is the set of all functions from z to z. Our operation is function addition. And then you can check that this actually is a group. Right? We've defined a binary operation, right? If f and g are functions from z to z, then so is f plus g. So that means that it's closed. So I'll just say that, right? S is clearly closed under plus. Let's see. It's associative. Why is it associative? Well, because addition. All right. So let's say it like this: plus is associative. And the reason is that associativity of addition holds for integers. So plus is associative because plus is associative in Z. You should go through and write up the details of that, but that's the reason behind it. Who's our identity function going to be? Function, I didn't give it a symbol. What should we call it? E maybe? E from Z to Z, defined by E of n equals 0 for all little n in Z is an identity. For S. And then inverses, given, let's say f in S, note that the function minus f from Z to Z, defined by minus f of n equals negative f of n. So what do? You take n, plug it into f, and then negate it. Right? That's how this function minus f is defined. So this is an inverse of little f. So what's our conclusion then? S, together with the operation of addition, is a group. Okay. I want to modify, or I want to do a sort of similar type example now. So next example, let's let S be the same set. So S is the set of functions from Z to Z. So same set as we had, but now I want to consider the operation of composition. So now consider, it's a binary operation, right? So consider the binary operation circle, right, which is composition. So if you take two functions from Z to Z and compose them, you get a function from Z to Z. So that tells us, so S is closed under composition. Composition is associative. If you took my Math 248 class last year, I have a bunch of you that took it last fall, and at some point we showed that composition of functions is associative. And then I said, you know, this happens every time I'll teach 248, we'll talk about composition of functions being associative, and then I'll say, hey, you're going to need this fact later on when you get to Math 148. Now we can just write it down, we don't need to prove it. Composition, or in fact, let's just use the symbol circle. Circle is associative. You learned this in Math 248. What's next? So now we need an identity. Who would be a good identity? The function I used E before, so let's just use something else. How about H? H from Z to Z, defined by H of N. Maybe H is not the greatest choice. H of N equal to N for all N in Z is an identity. Notice my formula for identity is different. Right? When we were doing the operation of plus, my identity was the function that spits 0 out every time. That was my function E. Now my function H, every time you plug in an N, out comes N, right? That serves as an identity in this case, right? Because we've changed the operation. And I want you to go through and check this, right? Right? This is a good exercise right here to verify that it serves as an identity on this set when we're working with the operation of composition. Please go and check these things. We don't have time to check every single one of them in class, right? But as you're studying your notes, right, these are the things that you should just quickly check. Last thing. So now we need to check inverses. Okay. So let's see. Wait a minute now. Okay. Let's think now. There's another 248. I was going to kind of just work my way through and get stuck, but there's no point in doing that. Under this definition, this is the typical definition of identity function for a set. And what do we know? What did you learn in Math 248? A function has an inverse under composition if and only if function is a bijection. Right? So as soon as we have a function that's not a bijection, so let's say note that the function f in capital S, defined by f of n equals n squared, has no inverse. So what do we know here? By changing the operation, we get, right, a set with a binary operation. It's closed. It's associative. It has an identity. but inverses, the inverse axiom does not hold. This set right here, S, with the operation of composition, is not a group. So how can we fix this? How could we get a group of functions from Z to Z that is a group? Well, if we restricted ourselves to bijection. So as the next example, let's let T be the set of bijections from Z to Z. All right? Throw out ones like this that don't have inverses. Then, all right, so then T is a group under composition. Let's do a few more examples and then we'll call it a day. And in these ones, I would like you to just go through and check the details. All right, but we need to build up our list, our collection of groups. So M sub mnr, or m by nr, this is the set of m by n matrices. All right, so this is a group under matrix addition. All right, check that. So this is a group. Next example, so now let's look at m sub n by n. Actually, I just want to use a single n here, mnr. So who is this? This is the set of n by n matrices with entries in R. And you can go through the properties. So now under matrix multiplication, let's see, if you multiply two n by n matrices, you get an n by n matrix. That tells us that it's closed under multiplication. What else? Associativity, you know from Math 206 that matrix multiplication is associative. Identity, well, the identity matrix, the one that has ones along the diagonal and zeros everywhere else, that will serve as a multiplicative identity. And then what do we need? Inverses. Not every matrix is invertible. All right, so it fails inverses. So this is not a group under multiplication. It is under addition, right, because of this up here. But it fails the inverse axiom, and so how could we fix that? How could we get a group of matrices under the operation of multiplication? Well, why don't we just focus on the ones that are invertible? And so here is some standard notation. So GLNR denotes the group of n by n invertible matrices under multiplication. So anytime when we see this symbol right here, we are talking about the group of n by n invertible matrices under the operation of multiplication. Let's end with this definition here. So a group G is abelian if, let's say, G star H equals H star G for all little g and little h in capital G. So if you can perform the operation in either order for all possible choices of elements, then you say that the group is abelian. And this word here, abelian, comes from one of the early, I can't say the founding father, but one of the early guys who studied and developed group theory. His last name was Abel. And so that's where we get abelian from. It's named in honor of him. Sometimes people will say commutative, but so commutative group is sometimes used, but really abelian is the standard terminology. So I guess I could say also known as commutative. Group. Right, but abelian is definitely the more standard terminology when you're working with groups. As an example, there's lots of examples. So Zn is abelian. There's also lots and lots of examples of non-abelian groups. GLNR is not abelian. Okay, so that's a good place to stop. We now have a good sized list of groups to work with, and yeah, in fact, that's a fairly large collection, right? And this encompasses many of the groups, not all, but it encompasses many of the examples of groups that we're going to work with in this class. Okay, so we'll see you next time.